Okay, so we're done with continuity equation. We will still use continuity equation later. Huwag yung kakalimutan yan. Kailangan siya sa Bernoulli's equation. And now we'll go to Bernoulli's equation. So that's our second equation for the day that we will derive. So the Bernoulli's equation basically ganito. Let's assume that we have an ideal fluid. Again, the Bernoulli's equation is only true for an ideal fluid. Huwag yung gamitin sa kung saan-saan yan. Let's first assume that it's an ideal fluid. Then, of course, since let's say that we have a column of fluid that's and we consider two cases here. Initially, we have this fluid column here, and then it moves. The fluid column or fluid volume moves with some displacement ds1. And then, of course, since incompressible ang fluid, ideal to eh. At some point, at a point higher than the initial point, di naman kailangan higher, pero at some point, some other point inside the fluid column, another column of fluid will move with some displacement ds2. Okay? And of course, pwede ka mag-apply ng force dyan, which is given by P1A1, where P1 is the pressure at the bottom, P2A2 is the pressure at the top. So you have this force here, and you have this force here, P2A2. So there's some external force that's acting on each of the fluid columns. And then after that, syempre may velocity yan, this fluid zero some velocity, let's say V1 at the first point and V2 at the second point. Now, anong mangyayari? So, you can think of it this way. Pwede mong isipin, meron kang differential volume dV here, and therefore you can calculate the total work done, the kinetic energy, and the potential energy on these fluid columns here. So for example, the work done is simply force times displacement. Force times displacement, we're assuming that it is a straight line, therefore wala tayong issues sa dot product natin. Pero in general, hindi kailangan. Pero differentials naman to, so the angles won't matter that much. So this is just the total work done by the pressure. This is force times displacement minus force times displacement. That's the total work done on this fluid parcels here. And then after that, so in that case, since area times displacement is volume, then the total work, differential work here is just a change in the pressure times the differential volume. So P1 minus P2 times dV. Okay? The P1 here is upward, the P2 is downward kasi kinokontra niya yung motion ng flow. Okay. Now, then the kinetic energy is just equal to 1 of mv squared. But this m here can be written as density times volume. And hence, it looks like this. This here is the total mass dm of the fluid column or the fluid parcel. So this is just simply rho dv. Okay, and the total kinetic energy is just the change in the kinetic energy at V2 and at V1. So this is a kinetic energy at V2, and this is the kinetic energy at V1. So this is some K1. Okay, and then finally, since may change in height ka, of course, meron din dapat potential energy, and in particular, gravitational potential energy. So the gravitational potential energy is simply mgy. But m again here is differential, maliit na volume yan eh. So that's differential mass. So meron kang parang mgy, pero instead of having mgy, you have gy times differential of mass. But that differential of mass is simply density times this infinitesimal volume. So therefore, you have a potential energy that's given by the total mass times acceleration due to gravity times the change in height, where the total mass is rho dv. Okay, that's differential mass. Okay, rho dv. Nakuha? Questions? Nakuha to?
Yes, sir.
And then, we know that since wala namang energy loss na nangyayari dito, ideal fluid, walang viscosity, then we say that conservation of energy is true, and therefore we can relate the total work done by the total differential kinetic energy and differential gravitational potential energy. And hence you get this relatively long expression here. P1 minus P2 times dV equals that kinetic energy term plus that potential energy term. Okay? And lahat sila may common na differential volume. Di ba? May common na differential volume. And hence, you can remove that differential volume. We are assuming that dV is not zero. It's a very small quantity, but it's not zero. You get something like that. And then, therefore, we get this equation here, or pwede mong ganyan, or this very large expression here, which is also known as your Bernoulli's equation. Malinaw? Clear ba to?
Yes, sir.
Sir, paano kakabisaduhin yan? Actually, mas gusto ko tong form na to. I like this form better kasi mas madali ko siyang maisip. Pwede mo kasing isipin na ang Bernoulli's equation ay conservation of energy per volume. So for example, this is potential energy, right? This is the potential energy per volume. Kaya may density ka dyan. Mass per volume is density. Similar to this is also kinetic energy at 1. So kinetic energy per volume, density yan. Nakuha? And this is also work. Pero work per volume is sort of, it has the same unit as pressure, P1. And this is the total energy initially, this is the total energy at the final state. Nakuha? So mas gusto ko tong form na to kaysa dito sa actual final form. Pero mas madali itong gamitin sa problems if you memorize it. But I memorized this first equation more, to be honest. Okay? Nakuha? Questions? Again, the Bernoulli's equation is an energy equation per volume. Nakuha? Yun lang isipin nyo. Energy equation per volume. Conservation of mechanical energy lang to. Pero per volume siya. Okay? Questions? May tanong? Wala?
Wala po.
Wala. Okay. Now, before I forget, we will also use continuity equation in solving problems involving fluid flow. So magkasama yung Bernoulli's equation at saka continuity equation sa mga problems. So wag na kayo magugulat pag kailangan nyo minsan at the process mag-continuity equation. Okay? Sige.